A finite-state machine, abbreviated as FSM, is a sequential circuit where the flip-flops have a finite number of states, which are represented by the output value of each flip-flop, and the transitions between each state are well defined. A counter is a simple type of finite-state machine. In the case of a counter, the flip-flop outputs collectively describe the number that the counter circuit is counting at that moment in time. In general, finite-state machines have output values that do not necessarily have any specific meaning, but which are used to define a particular circuit state. There may be one or more input signals used to transition between states, and there may be one or more output values used to denote a particular condition of the circuit. The number of flip-flops required in a typical finite-state machine circuit is equal to the number of bits required to represent the number of states. A finite-state machine with 4 states would require 2 flip-flops to implement. A finite-state machine with 10 states would require 4 flip-flops. If there are n states in a finite-state machine, then the number of flip-flops required is the ceiling of the log and base 2 of n. Each of the states in a finite-state machine should be clearly defined. A reset state that corresponds to an idle or reset condition should be included in the list of states. Because flip-flops may initialize with random values, it's important to ensure that the reset state can be asynchronously entered by using the clear pins on each flip-flop. If using a flip-flop chip without asynchronous clear pins, then careful design needs to go into the flip-flop to ensure that a random initialization value won't cause the circuit to act in an undesired manner. Each state and the transitions between those states are represented by a state diagram. Because a finite-state machine may also have output values, those also need to be represented on the state diagram. We'll see how that's done for each type of finite-state machine in their respective videos. The transition between states are described with arrows, which may include input values to represent how the input affects the transitions between states. A state table is derived from the state diagram. This contains the exact same information as the state diagram, but is represented in tabular form. It makes it easier to carry out the subsequent design steps. Once the circuit designer has a well-defined state diagram, the flip-flop type should be selected. There's not necessarily a best type of flip-flop to use, although we may consider rising or falling edge clock trigger as an important design decision. We may also look at our transition table to help determine if one type of flip-flop stands out as being more beneficial than another. And, as mentioned previously, due to the abundance of don't care values, JK flip-flops do tend to lead to simple expressions, although there are twice as many expressions with JKs as with D or T flip-flops. Then, the circuit designer will define state assignments for each state. This is a binary value assigned to each state and will be represented by the output values on each flip-flop when the finite-state machine is in that particular state. These assignments are mostly arbitrary, except that the reset state should be defined with a state assignment of zeros, so the asynchronous clear pins can be used to enter the state at any time. Then, a transition table can be defined. This can be used to derive next state and output expressions for the finite-state machine. We'll do many examples of this design process to really see how it works. As with counters, all finite-state machines are deterministic. This means that the circuit will go through the exact same transitions given the same current states and input values. If provided with a circuit diagram or given enough time, an engineer can derive the state diagram of the circuit, and the circuit will follow that state diagram. The two types of finite-state machines are Moore machines and Mealy machines. Both of these finite-state machines have similarities and differences in their designs, and we'll discuss both of them in detail in the next 2 videos.